That's good. Physics is good. Yeah. I used to, when in high school, I did the physics competition, and I did very good. So that's why I skipped the standard test in my country and get some positions here at university. So yeah, I used to be a physics major student. I then switched to math, and finally get a PhD in computer science. But I will see all my research about mathematics. Well, just as I said, I consider myself as a mathematician, but it seems like most of my colleagues doesn't agree, so they still consider as a computer scientist. But anyway, so today I'm going to give you like 45 minutes. Yeah, something like a quick introduction to quantum computing, especially for some like what is a qubit, what is a quantum gate. And the most important thing before introducing these fundamental definitions, I want to introduce what is quantum computing. You probably talked about it before, but I also want to talk about some from my perspective. So quantum computing to me is like a brand new computing method based on these new discoveries in quantum mechanics. Well, it's not very new discoveries, over 100 years ago, but compared to the history of math and physics, it's quite short. So like superpositions, entanglement, and decoherence, all these very famous phenomena. Based on this, we can achieve an exponential speed up compared to a classic computer. So what does this mean? So let me give you an example to explain this one, so maybe it's more straightforward. The most famous problem in quantum computing will be the factoring problem. So factoring problem is, well, I haven't used that for a really long time. So a factoring problem is giving you a very large integer, okay, any integer n. By the fundamental theorem of arithmetic, for any positive integer, it can be decomposed as a product of prime numbers. Right? For example, 12 is equal to 2 times 2 times 3. Right? 2, 2, 3, all these are prime numbers. And the most important thing is this decomposition is unique. That means if 12 can be represented as 2, 2, 3, there's no other ways you can represent 12 as another another sequence of prime numbers, 5 times 7 or something. No. If it's a 2, 2, 3, then 12 is uniquely determined by 2, 2, 3. Okay, so that means like for mathematician, especially mathematician working on algebra and number theory, so they don't recognize 12. To them, 12 is equivalent to 2, 2, and 3. So any integer is just a sequence of prime numbers. Right? And that's also why the prime number is so important in number theory. And then you can imagine that if we understand the prime numbers very well, you will understand the integers very well. Right? Because there's no difference between prime number and integer. Integer is just a sequence of prime number. And if you understand the integers very well, which is a z, the next thing you're going to understand very well will be q, which is the set of rational number, because by definition, rational number is just a quotient of two integers. If you understand the rational number very well, next thing you're going to understand all real numbers very well, because rational number is dense in real life. That means for any irrational number or any real number, it can be approached by a sequence of rational number. And if you understand the rational number very well, complex number will be there. And as you can see, complex number is a fundamental number for the quantum mechanics. If you know the quantum, if you understand the complex number very well, you most likely gonna understand the whole world. That's why we said that the prime number is so important. But unfortunately, we know very little, very little about the prime number. And the one of the most famous conjectures called Riemann hypothesis is talking about the distribution of prime number. Well, it's too far from quantum computing. But what I want to say is this problem is a very famous problem that is from giving you any integer to decompose to be a sequence of prime number, it will be a very difficult problem. 12 is easy. What if I'm giving you a 1, 2, 3, 4, 5, right? So, for this integer, can you write in the sequence p1 times p2 times into pk? Can you find the sequence of a prime number that the product is this integer? It will be difficult. Well, it's easy for a computer. But think about that, if you have a very large integer, for example, if you have an integer with over 250 bits, actually it's not a very large integer, but for such an integer, any classic computer in the world, even the most powerful, supercomputer in the world can submit, they cannot handle this problem. For any integers bigger than this one, not exactly bigger than this one, but around this like 250 or 300 this long of integers, there's no way you can break to be a sequence of prime number. So that's a very simple result, but this hardness is so hard, this problem, and this hardness is used to protect our bank account. And we use this one to design RSA crypto system, the very, very famous crypto system. So every day you're, probably not every day, but when you swipe your credit card, sending to buying something online, you're sending your credit card number to the stores. During this transformation, they're using RSA crypto system to protect your information. And they call it the public key crypto system. Most of the public key systems are based on this very simple, very simple math fact. That is, for a large integer, it's very difficult to break to be a sequence of a prime number. But in another way, we know this way is extremely difficult. But this way will be extremely easy. That means if I'm telling you this sequence of a prime number is the answer, it's very simple to verify that. Right? So then what does it look like? This just looks like my office key. If you do have a key, very easy to get in my office. If you don't have this key, if you got in my office, you have to break my door. That will be difficult. That's how we use a computer to simulate a real key in my office. That's called public key. If you have some other problem similar to this one way is very simple, another way is extremely difficult, you can also use this as a core function to design your own crypto system. But this is the most popular system. Back to this quantum computing for this very famous stacking problem. If we do have a very powerful quantum computer, and what I mean by the word powerful quantum computer, that means you have to have a qubit. We'll explain what does qubit mean, but you can currently imagine a qubit just like classic bit. It's a unit information in quantum world. So if you have a qubit with a 10 to the power 6 qubits, if you have such a number of qubits quantum computers, currently I think the most powerful quantum computer have less than 10 to the power 3. Less than that. Hundreds of them. Okay? But if you have a quantum computer with a 10 to the power 6 qubits, that means for any stacking problem, you can break it in just a second. So that means no RSA crypto system, any public key system, crypto system will no longer exist. So you can break any people's bank account in just a second. Okay, so just one example to show you how powerful is the quantum computer. But there's some requirements, that is you have to have a very powerful quantum computer with a 10 to the power 6 qubits. Currently we are trying to reach this limit. Okay, it's still far away, but as you can imagine that if you look at the history of the development of a classic computer, 50 years, right? From nothing, a very huge computer like this room big, until we have something in the hand, 50 years. How many years do you think from 10 to the power 3 to 10 to the power 6? I will say it's less than 50 years. You will break all the crypto system in the world. And the corresponding quantum algorithm we call Shaw's algorithm is proposed by a professor at MIT, Peter Shaw. He's still alive. Okay? So very famous professor, Shaw's algorithm is to break this stacking problem. Okay? So that's why we need the quantum. We need to study something like for the quantum computing. Okay? And unfortunately, I don't have enough time to discover more stories about quantum computing. But if you are interested, you can just talk to me. Okay? Okay, any questions so far? Yes?
What's the Z and the Q?
Oh, Z is a set of integers. This Q is a set of rational number. This is a set of real numbers. This is all complex number. Yeah. So all the quantum mechanics, like Schrödinger's equation, the very fundamental, most fundamental equations in quantum mechanics will involve in some imaginary units, like a complex number here. If we have time, I will talk about why we need complex number in quantum mechanics. Some people think that for quantum mechanics, the complex number is just a technique, math technique. That means I'm using the complex number to make my whole description of this word simpler. But actually, no. So real number cannot replace a complex number. And people just proved this one few years ago. It seems a very difficult problem. Okay? So again, so people think that, well, we have a quantum mechanics, all the knowledge we know over 100 years ago, right? And all the things you learn from the class is all in complex number. But people believe that we can still use a real number to replace the complex number. The complex number is not necessary to describe the quantum world. But people always believe that until a few years ago, people proved that no, it's a big no. Complex number is necessary. Even we cannot see it. The reason why people think the real number can replace the complex number because everything we can see in the world, everything we can measure, every outcome we can get is all in real number. Complex number, by the name of complex number, like an imaginary unit, I, is something does not exist. Right? We create from a square root of negative 1, so something does not exist. And we think since it does not exist, it just helps us to make to give a better math description, but it's not necessary to describe the world. That means if we want, we can use a real number to replace all the knowledge in the quantum mechanics equations. But as I said, it's an extremely difficult question. People just answered it a few years ago. And that quantum, they designed very special experiments to show that for this special experiments, if you only use a real number, it's not necessary. It's not enough. You have to use a complex number to describe it. That paper is published in probably less than 5 years ago in Nature, so it's a very important paper. And yeah. Okay. Yeah. Any other questions? Okay. Great. So let me just do this. That's why I'm wearing a mask. I'm using it for okay, so now you know from this example, you see how powerful is the quantum computer, right? Or the quantum computing method. And there's another thing I want you guys to know. I mean, even you don't understand every details of what I said in the following paragraphs, but I still want you to know that is the limitation of the quantum computing. We all know the quantum computer is so powerful, can do this, can do that, can solve in the RC in just a second, something, but there's still some limitation for quantum computer. The most important, the most limitation for quantum computing, I think, will be the compared to the classic computer. Classic computer is everything you can see, and if you input some for example, if you input like 100 information, you should get 100 information back, 100% information back. But for quantum computer, it's something different because the many things in the superposition, and because of the measurement principle we'll talk about later, every time you measure things, you only have just a single point back to you. So that means, for example, the most famous example will be called quantum Fourier transform. And you learned that in my class. So for that, the quantum Fourier transform one is called classic. After you do the matrix multiplication, you will get the whole matrix. That's a matrix called 2A times B. So for classically, even it's very slow, but after you do the calculation, you will have the whole information of this matrix. But for quantum computer, you can do this matrix multiplication very, very efficiently, exponentially faster than classically. But you only can receive one single piece of information. All others you don't know. If you want to know the whole picture of this matrix, you have to repeat this quantum computing process again and again until you get all this information appear. And this process will be equal to the time complexity of classic computing. So that's what I want to see. So classic quantum computing, yes, it's very efficient, but less information you can get. For some special problem, you don't have to know, like this is a quantum Fourier transform problem, QFT problem. You have to know the whole information of the matrix. If you want to know the whole information of this matrix, then no matter it's classic or quantum, it's oversold. But for some special problem, like the short stacking problem, the stacking algorithm, you only need to know probably just a single piece of information will be enough. Then the quantum computer will be showing their powerful computing speed. Okay, so that's some limitations. But you have to know what is the QFT means. Then you understand what I'm talking about here. But I'm just telling you. This kind of a trade-off, okay? So nothing is very perfect in nature. Okay, you get a very fast computing method, you get less information. If you want to have a computing method with exponential speed up, and also you want to get a whole information, that's impossible. Yes?
So in some sense, there's like quantum computers and classical computers on like two different sides of a trade-off.
That's right.
You have their speed and their information.
Yeah, that's right. So that's what I'm thinking that I think for the future, even we have a very powerful quantum computer, the quantum computer usually going to design only for some specific problem. It's not like my iPad or the laptop, we have a CPU can handle all the calculations. All the kind of problems can handle by my CPU. But for quantum computer, quantum CPU, I will think the next generation of computer will be the hybrid computer. That means most likely will be classic, but for some very difficult problem, we'll call the quantum CPU to do that. But for the general, like the task, we'll just use CPU. Except we're meeting some very difficult problem, like a factoring problem, matrix multiplication problem, a very difficult exponential NP complete problem, then we will call the quantum CPU. Otherwise, we will just still continue to use the CPU. So I think the next generation will be the hybrid between the CPU and the quantum CPU, something like that. And actually, the very popular research topic in the quantum computing will be called quantum machine learning. And if you take a look at quantum machine learning, they all hybrid. They're not purely quantum. They are hybrid quantum. So the first thing to do, you're going to compress the whole data set to be a 4x4 or 8x8, or small image, and fit them to the quantum like a machine or something. But the post-processing part is still classic. As there's no like a purely like a quantum machine learning. It's all hybrid. That's what I think. Okay. So, all right. Yeah, so that is the advantage and disadvantage of the limitation of the quantum computing. And next, we're going to start with talking about the basic fundamental, like the definitions, or the simple we call building blocks for quantum computing, like what is a qubit and what is a quantum gate. Okay, so the qubits, and just look at the vocabulary here, the qubits obviously is a very general, very natural generalization from bits. Right? So the classic bits, we know, is just a unit information for classic computers, and we sometimes using like hydrogen atom to represent a classic bit, right? We have a nucleus here, and we have different level of energies. Usually for this one, we have two different level of energies. So the first is called ground state, and the second called exciting state, right? It's very fundamental definition in physics, right? So this is called the ground state. And this is the exciting state. Right? Then we use a special machine to converting this ground state to be, let's say, 0. And we encode this excited state to be just a classic 1. And we know that for the classic bit will be either 0 or 1. We have two different levels of energy, so it can only be in this orbit or this orbit. It cannot be like in the middle of them. It's a discrete energy level, right? So each one is corresponding to either 0 or 1. So that is a classic bit, and the most thing I'm going to say the binary strings, like 0, 1, 0, 1, 0, 0, 1, 1, something like that, right? For each bit, it corresponds to an electron in different energy level. That's a classic way we do the computer, right? But if you think about this state in the quantum way, what does that mean for the quantum state? Or just in short for the qubits. So that means how we're going to measure the unit information in the quantum world. So that's how we measure the unit information in the classic world. In the quantum world, similar to this one, we have a hydrogen atom here. We have two different levels of energy. Okay, the only difference here is for classic one is you only allow the discrete energy. That means it will be either 0 or 1. It cannot be both. It cannot be middle of them. But for classic world, we cannot break this rule. We are allowing to have some energy kind of between these two energy levels. But of course cannot jumping out. It will be bounded by 1 and the lower bounded by 0. It will be something between them. And of course can be 0 or 1. If it's 0, to distinguish the 0 as a classic 0, we call this energy level called this 0. The Dirac notation or bracket notation to denote this one. This one we call 1, but we use this one called cat 1 and cat 0. This is called Dirac notation. Or the bracket notation. It's just a notation to represent the vectors in the quantum space. And again, just as I said, instead of the discrete levels, the quantum state can be in between 0 and 1, can be anything between 0 and 1. So that one we also call another word called superposition principle. That's the first important principle in quantum mechanics or the quantum computing. So mathematically, how do you describe this phenomenon here? What does it mean for between 0 and 1? So that means for any quantum state, we call it phi, cat phi, for any quantum state in general, it will be equal to the linear combination of 0 and 1, because it's between 0 and 1. And then the coefficient between 0 called alpha, the coefficient between 1 before 1 we call beta. And the most important thing is alpha beta is not just arbitrary two numbers, they follow some special constraint that is alpha squared plus beta squared will be equal to 1. So that's how we describe in a generic quantum state. It's always between 0 and 1. Mathematically, we're using this equation to describing what I draw pictures here. But this superposition principle is only in a very different word because this is in a different word that we cannot see it. That's only in, it's just like our I is equal to square root of -1. We cannot imagine, we cannot picture it. It's just some kind of imaginary parts. But here is we also cannot be in an imaginary space because the next following principle for quantum computing will call the measurement principle. So the measurement principle is talking about if you have a quantum gate in the superposition, as long as you measure it, you see, if you don't look at it, it will be in the superposition. It will be probably halfway of a 0, halfway of 1 in the middle of them. But as long as you look at it, you measure it, it will be jumping to either 0 or 1 with a certain probability. And the probability will be the coefficients right here. So that's called the measurement principle. That means if you measure it, no matter how you measure, you use some special detectors, or you just use your eye to see it. As long as you measure it, you get some information come back from this object, this will break the superposition principle. It will come to the classic world again. So after you measure it, we'll have with the probability to be 0 will be alpha squared. The probability to be 1 will be beta squared with their coefficients here. So they have, for example, if my alpha here is, 1 over half square 2, beta is 1 over square 2. So first, alpha squared plus beta squared is equal to 1. Second, that means after you measure it, 50% you will get 0, 50% you will get 1. In this picture, that means this state is somewhere in right here between 0 and 1. But just as I said, this state does not exist if you see it. Once you see it, will jump into either 0 or 1 with half probability. But you can always control this alpha and beta to be different numbers. Right? You can make it to be like more closer to 0 or closer to 1. Right? So tell me how many combinations of this alpha and beta here? If this is the only constraint I have, this is a linear combination of this one. That means that between these two, discrete energy level, and the only constraint here is alpha squared plus beta squared equals 1. Tell me how many solutions for alpha and beta? There's infinitely many, right? There are infinitely many different solutions for alpha beta because it's only one constraint. Unless you add another equation, you will have a definite solution. But if you only have this one constraint, you will have infinite definite solution for alpha beta. That means it can be anywhere between 0 and 1. And actually, if you draw a picture of the single qubit, it will be a very famous ball called the North Sphere. If the North Pole is 0, this is 1. So that superposition means it can be anywhere on this sphere between 0 and 1, anywhere. Or you can think about this discrete orbit anywhere between these two energy levels. Both of these principles are very fundamental principles in quantum mechanics and also quantum computing, and both of these principles are very counterintuitive. Right? You cannot see it. You can just, it's like a science fiction, right? So it's not true. I mean, it looks like, if it's not like a real physics to give you the theory for quantum mechanics, if it's just arbitrary people tell you these two positions, you will think that they're crazy. Right? But actually, they are indeed true. Well, currently we think it's true, but probably after another 100 years, we will show that quantum mechanics is not true. There's another theorem covering it. But currently, we believe these two principles, even it's very counterintuitive, even we cannot see it. That's why some people like Albert Einstein, he doesn't believe it's true, right? And, I think 2 days ago, right, so we have the Nobel Prize for Physics. Yeah, for the quantum prize. The reason why we gave him the Nobel Prize is because we did some special experiment to show that Albert Einstein is wrong. This is correct. Yeah. But as I said, so if you look at the history of the human, over 2,000 years of history of human, right? Currently we think it's true. After another 100 years, we'll prove this is wrong. It's very possible this theory is wrong. Right? So it's we're moving forward. That means if people are moving forward, that means we have to say say no to our path. Right? So that's how we push the science to go forward. Right? So again, but currently we believe these two principles, and these are the fundamental principles for the quantum computing. Okay, and with these two principles, we also explain what is the qubit, right? It's more like you can think about that it's like a generalization of classic bit. Classic bit can be only discrete. Classic bit is just like Classic gate is just like integers. It's discrete point. Quantum gate is more like real numbers. And it's continuous. Right? Think about the history of we expand the number system. Z, Q, and R. Next will be complex number. The question is, do we have another generation for the qubits? Do we have a next object? More generalized than this one. This leads to you guys. Okay? Alright, so any questions so far? Yeah.
About the Morse code and Self model, does it mean that it is more likely that alpha and beta are equal?
You mean if it goes here? If it goes here, that means alpha will be 1.
I mean, like the
Beta will be 0.
is like just it's like very unlikely for either alpha and beta is equal to 1, but it's more likely that alpha and beta is equal to like 1 over square root of 2.
That's a good question. I mean, seems like for this sphere, it looks like the middle circle will be bigger, right? But that's not true. I mean, so again, so medicine in the quantum computing is counterintuitive. Alpha equal to any number and beta equal to another number will be uniformly distributed on this sphere. Okay, so the probability to appear right here is same as probability to appear right here. Yeah. That's also because if you have bigger circle, for example, if you make the big circle is like this length, it looks like this one is shorter until right here, right? That's how you view a sphere, right? But the John Counter 150 years ago, he proved that even for two different lengths of lines, we can find the bijective function between these lines. In other words, infinity plus some constant number is equal to infinity. Or infinity plus infinity is still equal to infinity. That means even looks like it's shorter than this one, but we can still build the one-to-one and onto mapping between these two. That means they all have the same probability. That makes sense? Yes. So as you can see, this is a very good question because if they are not this, if you don't have this bijective function between these two lines, that means the probability on this sphere is not uniform. It has some bias, right? It's just because John Counter proved this is true, right 50 years before the birth of the quantum mechanics, then we can do this kind of theory. Okay, so again, my favorite book is a history of the math book. I have a sequence of the book called, I don't remember the name of the book, but it's just called some history of math. So that's a very heavy book. And if you look at this book, not all the stories, just pick a random story, read it. Very simple result in your textbook, no matter from discrete math, from linear algebra, very simple theory, they have a very rich story behind it. And you can see that before this story, before this people proving this theorem, you have to know some previous knowledge like this one. Then you can do this. Then the next one you can do nonsense. So that's always a sequence of stories. Very interesting book. And yeah. And after you read some of the stories in the history of math, you will see everything you learn in the college right now, everything in the textbook may not be true. People are going to prove it wrong maybe in the next few years. Not everything in the textbook is true. I will see many of the things will be wrong in few days, but not few days, probably in few decades. Okay? That's also we call it critical thinking, right? As a college student. That's also make a difference here. Yeah. Any other questions? Okay, very good. And I think the last thing I want to talk about is a quantum gate. So the quantum gate, again, just like the word, you can imagine that they just correspond to the analog to the classic gate, right? So for the classic logic gate, before we talk about what is a quantum gate, that's a very important thing I want to let you know that is for the classic gate, like the OR, right? The AND function, or negation, right? So that's a very fundamental classic gate. We have a very finite number of classic gate, right? 3 of them. The most difference between the classic gate and the quantum gate, mathematically, we have a finite number of classic gate, but we have infinitely many quantum gate. Infinitely many. Because in quantum computing, classic gate is nothing special but just a unitary matrix. We'll talk about it later. But now just need to know that there is an infinitely many quantum gate. That means the bigger playground, you can create many of very creative, many of interesting circuits in the quantum world. Okay. Yeah. So we will start with a very fundamental gate in quantum. We call it quantum NOT gate. Because this one is very similar to the classic NOT. It's called quantum NOT. And in classic NOT, you know, it's just a swap 0 and 1. If 0 goes to 1, 1 goes to 0, right? Simple. What does this mean for this swap 0 and 1 in quantum way? Think about that. Is it possible for you to create this quantum knot yourself? So think about that. So why we swap 0 and 1? Because 0 and 1 is a unit information in a classic computer. What it not gate just reflects the unit information in the classic computer. What is the unit information in the quantum? This. Right? Just a state. A qubit. How can you swap 0 and 1 in the analog to the classic knot?
So it comes beta.
Say it again? That's right, exactly. We just swap the alpha and beta. That means we set the probability of 0 and 1. Think about that. If your alpha is 0, like if alpha is 0, beta is 1. It's just an extreme case that your phi will be just 0, right? So after applying a knot, you should get 1. It's exactly swapping the alpha and the beta. So same thing here, if the alpha beta is both non-zero, you still swap it. For something like this one, a special one, if you swap the alpha beta, will be remain the same. Right? This does not exist in this classic bit, right? This classic bit, this swap it, you have to change the 0 to 1, 1 to 0. But it's possible for quantum, the single qubit, even if you swap alpha and beta, you still get to remain the same. It has some kind of a fixed point. Right? And again, so that's what we talk about in English. So everything we want to transfer to be mathematics. So what does it mean in math? So that means if you will this qubits in different way, if you will this like the 0 and 1 as the 0 and 1 as a computational basis, that means it's just a 2 bases, and this one will be a vector of 0 and 1, right? So that will be something like this will be 1, so that will be 0, so alpha 0 plus beta 1 will be just some vectors, right? If you will this qubits like vectors, and in this way, we can assign this 0 as a classic vector like 1, 0, and beta we will assign as 0, 1. Because there's nothing special but the 0 and 1. Oh, 0 and 1. The 0 and 1 are just like orthogonal like bases, right? So we can just think about as 1, 0 and 0, 1. Right, in this way, that means my phi here simply just alpha 1 0 plus beta 0 1, which is just alpha and beta. Right? And the norm of this vector is 1. Right? Because of alpha squared plus beta squared is equal to 1. That's also to ensure the probability. Why alpha squared plus beta squared equal to 1? I've got to explain this one because there's a probability of 0 and 1. It can be either 0 or 1. That's why when we add them together, it has to be 1. There's no other probabilities hidden event. There's only two possible events, either 0 or 1. So adding together will be 1. Right? So in other words, after applying the quantum NOT gate, this one will become to beta alpha. Right? Simple linear transformation. Alpha beta to beta alpha, so the NOT will be just a 2 by 2 matrix. What is that? What is a 2 by 2 matrix? Yeah.
0, 1.
That's right.
1, 0.
Exactly. Right? That's how we view this NOT gate from a math view. Right? Swap the alpha beta by doing some linear transformation, which is just this matrix. And actually this matrix is your quantum NOT gate. And yeah. And actually this is not an arbitrary matrix. This kind of matrix is a very special matrix. It's called unitary matrix. What does this mean? I mean, for the formal definition of a unitary matrix. How many minutes? Oh, it's already 45? Another 5 minutes, okay?
Does anybody have to? Well,
I see it.
it'll be recorded, so if you have to have one.
Well, you have to pay me some extra money for that. So I only be paid for 45 minutes. I'm just kidding. I'm here for volunteer. I mean, nobody paid me.
Well, you were going to be paid pizza.
That's what?
You were going to be paid pizza.
Where is the pizza?
Let's go. Let's go.
Let's go? Okay. Well, so talk to IBM to pay me some money at least. I'm just kidding. I'd like to talk this information, all this knowledge to you guys. It's very interesting. And just as I said, I mean, many things in your textbook is wrong. It's waiting for the next generation of engineers to prove it's wrong. Okay? I hope we can have students from Qiskit Western. We used to have very good history here in Qiskit Western proving something is really wrong. A very famous case right here. Right? So we can go on that one. So, where stop?
Unitary matrix.
Great, yes, unitary matrix. So, so any gate, so any matrix, if there is a unitary, matrix, that will be a quantum gate. For example, this NOT gate is a special unitary matrix. But in general, what does it mean for unitary matrix? For any matrix U, if U times U dagger is equal to the identity, the U dagger we call the affirmation conjugate. It's just applying, doing the complex conjugate. So after doing this operation, you will get an identity matrix. Then this kind of matrix will be called the unitary matrix. You can test it, it's easy, right? So that is 0, 1, 1, 0 times the conjugate, the affirmation conjugate, which is the transpose of this one, right? So 1, 0, 0, 1, something. No. 0, 0, 1, 1, 0 will be applied identity. This is verified. But again, as I said, any matrix satisfying this property will call a unitary matrix. And any unitary matrix will correspond to a quantum gate. That's something we don't have time to explain. But it's one more thing I want to explain is why we're using unitary matrix. So again, the unitary matrix is equal to quantum gate. So the question is, why we're using unitary matrix to represent the quantum gate? Why we're not using other properties of the matrix? We have many different kind of matrix. Why not just a general matrix to represent quantum gate, y has to be a unitary. Y has to be this property.
Is it because it preserves the one constraint that we have on alpha and beta?
Exactly. So that is one of the properties it has to satisfy. It has to satisfy is, as you said, alpha squared plus beta squared has to be equal to 1. So in other words, it preserves the length. It will preserve the length of the vectors. So that means if you have a vector like this, after you apply this one with a unitary matrix, it will become to direct to point to a different direction, but the length of the vector will remain the same. Because the length of the vector is equal to what? Exactly, the length of vector is equal to 1. This is the vector. You change from alpha beta to beta alpha, no matter how you switch, how you do the rotation, the length of the vector will remain the same. Preserve the length. Second important, it preserves the angles. It preserves the angles between any two vectors. Let's see the picture. If you have two vectors, we call them phi1s, another quantum state phi2s. If some special angles called theta here, after applying a quantum gate, any quantum gate, it rotates probably in this way. Phi1 prime, phi2 prime. But their angles will still be theta. Why do we want to preserve the length? Because of the constraint. We want their probability to be 1. Why do we want to preserve the angles?
Because you still want 0 and 1 to be as far away from each other as possible.
Say it again. So we
You
want.
still want 0 and 1 to be as far away from each other as you can.
Well, yeah, that's a very unique explanation. So yes, maybe, but another thing is if you take a look at the sphere, I mean every operations on the single qubit, any 2 by 2, the unitary matrix is just a rotation of the matrix, and the preserved angles will preserve kind of corresponding to the time series data in the physics. That means if you don't preserve the angles, you change the angles, you're going to disturb the time sometimes. That means, for example, this phi y happens in t0 time, and this happens in t1 time. If you don't preserve the angles, it may disturb the time. So that's more a very complex explanation, but this in general is something like that. If you disturb this angle, you will disturb the time space. Okay? So that's again, so I'm not giving you a lot of mathematical techniques here today. I'm giving you more like a high-level ideas and stories behind these definitions, why we're using this, and why we're doing that, and corresponding to all these definitions to the classic sense. Okay? And yeah, before we stop, I want to explain another two very important examples of a unitary matrix, or we call unitary transformations. The first unitary transformation you see most likely every day is called a Fourier transformation. Very classic transformation in the world, right? We're using the Fourier transformation everywhere in our devices to compress or decompress the signals, right? So that's using the Fourier transform. And if you take a look at the Fourier transform, it's complex, complicated formula like x will equal to the integral from 0 to infinity. Actually, sometimes we use a negative infinity to cos infinity. F of x e to the power of negative 2 pi I x s d of x. This is a Fourier transformation, and this transformation, if you want to prove it, this is a unitary transformation. And another unitary transformation that says, look at it here, preserve the length, preserve the angles. Okay? Preserve the length, preserve angles. It's already 8 o'clock. If you go outside and look at the stars.
Oh yeah, I had an astronomy class.
Yeah. The constellations in front of you, moving by the seasons and times is unitary transformation. It preserves the length, it preserves the envelope. For example, the big set, they call it Big Dipper, right? The Big Dipper constellation, something like, looks like this, right? Something like this, right? The Big Dipper, the sky, right? Is that? So no matter how it changes in the sky from 8 p.m. to 4 a.m. or from summer to spring, the shapes are always like this. That's because the constellation from that height here is unitary transformation. It's everywhere. And we use that to do the quantum computation. Okay, that's all today's lecture. Thank you. And I'm also looking for some undergraduate students in my research lab to do some research in quantum computer. Quantum computing, especially for the quantum circuit cut. That means we want to cut a very large quantum circuit because, as I said, we have very limited quantum hardware. We have maybe 100 or 50 or 20. But what if we have a very large quantum circuit that have 1,000 qubits here? So we want to cut this big circuit to be a smaller piece and run each smaller piece in a smaller quantum hardware. Then we do some post-processing in classic way to combine the result. The most difficult thing you can imagine that if you break the qubit, you will break you will measure it, right? You will break superposition. So how can you do that? And something like that. Yeah, that's some of my research. I mean, if you're interested, you can contact me, okay? And if you don't know my name, I will write down here, so that's my name. First name is Shuai, last name is Xu. So I'm a professor in the computer science department. Okay? But I work most likely in mathematics. Alright, great.